Audio Jungle.
Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 6, and for this video discussion of PBL Assignment 1, we will explain and present about the introduction of signal to noise ratio, which is SNR performance parameter. Then we will explain about understanding the given problem, explanation of brainstorm process to generate multiple solution, explanation on solution to the first and second question.
Assalamualaikum, my name is Muhammad Windy Afranto. I will like to explain for this problem-based learning activity 1, which is for the introduction for this project. Okay, this is project background. Our problem-based learning is about the communication system. Communication is the process of transfer of information from sender to receiver. Okay, the transmitter converts the information into the signal suitable for the communication channel, while the signals propagate through the channel. Noise signal arise. The signal along with noise will reach the receiver end, where message signal is filtered from the transmitted signal along with noise. To some extent, the noise signal can be filtered out and the message signal can be reproduced. So this is the basic block diagram of communication system. Okay, this is the signal to noise ratio, which is the ratio of the signal power level to the noise power. So this is a calculation for formula calculation for this SNR. Okay, for the figure table, we construct, which is we have facts, idea, learning issue, and actions. So firstly, for the facts is all the amplifier devices are portable for the task 1, which is, and second is for all chamber are non-portable, and third is input consistently 5-volt retrieve signal and bandwidth of 400 MHz. So next is the idea for this figure table, which is amplifier devices is used to increase the power, current, or voltage of the signal. The next for the chamber is had on the silence of protection. Okay, next is the input power source required to generate the output power value. Okay, next is the learning issues. Firstly is about which is the swapping the position amplifier devices can change the output of SNR. And next is, can the temperature of the chamber interfere the value of output of SNR? And next is what is the value output of SNR using the input with the chosen value of amplifier. Okay, lastly for action for this problem for facts for 1 and number 2 and 3, which is to calculate the value. So we want to prove the value for this task. Okay, that's all for me for the introduction. Thank you.
Assalamualaikum. My name is Muhammad Afiq Izzuddin bin Syarif. Okay, so here I will explain a little bit about PBL activities. Okay, for PBL activities, we have 2 questions. Okay, for question 1, what we need to do is to propose any practicable solution based on following condition and limitation. Okay, for question 1, we are given 3 amplifier and 3 chamber. Okay, for amplifier, they already give the gain for amplifier 1 4 dB, amplifier 2 5 dB, and amplifier 3 20. Okay, so for chamber, also given the temperature. Okay, for chamber 1, they give in Celsius, and the other 2 chamber given in Kelvin. Okay, so here we need to find the solution based on following condition and limitation. Okay, so next for question 2, we need to propose any further enhance the output SNR. Okay, so thank you.
Assalamualaikum and good morning. My name is Imran bin Muhammad Ghazali, method number CE190118, and I'm going to explain our group method of brainstorming the best possible solution for this PBL task 1. Okay, first we gather everyone in a Google Meet. Then we give each member some time to find the solution to enhance the SNR output and find the highest possible SNR output for each amplifier setting. And after some time we get the back and everyone present the results and the findings of the highest SNR output in the Google Meet. And after everyone has presented, we decide on the best possible solution. And after we have decided one solution, we continue on for the final report and video. That's all. Thank you.
Hi, my name is Amir Ali bin Shuhariman. My metric number is CE190028. In this presentation, I will explain for solution question 1. So, based on the solution question 1, there's a 3 type of condition where we need to calculate to get a best SNR output. So, there has 3 type of condition, which is condition 1, condition 2, and condition 3. The difference of these 3 condition is the value of the amplifier and environment temperature. So for amplifier 1, where we state the value that already given in the question. For the power signal input is 5 watt. For noise input is unknown because we need to get we need to calculate first to get the answer. And then the bandwidth is 400 megahertz. Environment temperature is 35 Celsius. Temperature in chamber 1 is 77 Celsius. And the gain for the chamber 1 is 4 dB, and their unitless is 2.5119. Okay, the first step where we need to convert 35 Celsius into the Kelvin. So the formula to convert Celsius to Kelvin, which is Celsius plus 273.15, so which is 35 Celsius plus 273.15, we get 308.15 Kelvin. And then next step is find the power noise input. So the formula for power noise input, which is K times T times B, which is K is stand for Boltzmann constant, and T is the temperature, B is the bandwidth. Okay, when we include all the value, and we get the answer for power noise input is 1.700988 times exponential negative 12. And then for step 3, we need to find the SNR. For the formula for SNR is S over N equal to power signal input times with divide by power noise input, which is 5 watt, divide by the value of P power noise input. We can get the answer is 2.939468121 exponential 12. Okay, and then next is step 4. Step 4 where we convert the unitless of SNR into the decibel, which we using 10 log 10 power signal input divide by power noise input. Then we get the answer which is 124.683 dB. And then for the step 5 where we need to find the noise initial, the same formula, which is K times T times B. Then we can get the answer of PND1 1.932828 exponential negative 12. And then next step is find power noise input P and out. The formula is PND, which is initial 1 plus with the gain 1 from the amplifier 1 times with the power noise input. So we can get the answer is 6.20552 exponential negative 12. So the next step is find the power noise output PS out, which is gain time with the signal input, or the signal input, which is 2.5119 time with 5 watt. We get the answer is 12.5595 watt. And then step 8 where we need calculate the output SNR for amplifier 1. So the answer is 2.030239 exponential 12. Then we convert to dB, we get 123.062 dB. Okay, then for the amplifier 2, where we state the information first, the power signal output 1 will be the input for amplifier 2, and power noise output 1 also will be the input for amplifier 2. So the chamber temperature for amplifier 2 is 300 Kelvin, and their gain is 5 dB, and their unitless is 3.1623. Then the first step where we need to find the initial noise 2, the formula K times T times B, we get the answer is 1.656 exponential negative 12. For step 2, we need to find the power noise output, same, which is PND of 2 plus with the gain 2 times P noise out 1. Then we get the answer is 2.12797 exponential negative 11. Then step 3, we need to find power noise output, where the gain 2 times with power signal out 1, we get the answer is 39.7153 watt. Then the step 4 is output SNR 2, which is power signal out divided by power noise out. Then the answer of SNR for chamber 2 is 1.8663 times 10 exponential 12. Then their dB value is 122.71 dB. Okay, next for the amplifier 3, we state the value that already we get from the amplifier 2. The power signal output and power noise output will be the input for amplifier 3, and the temperature of chamber 3 is 450 Kelvin, and their gain is 20. Then we repeat the same step, which is we need to find the power initial noise. We get 2.484, and then step 2, we need to find the power noise output, which is PND3 plus gain 3 times power noise out 2, we get 4.28078 exponential negative 10. And then step 3, we find the power noise output, which is gain 3 times with the power signal out, we get 794.3 watt. And then lastly, step 4, we calculate the output SNR for amplifier 3, which is power signal out divide by power noise out, we get the 1.8555 exponential 12, and their decibel value is 122.68. Okay, for condition 3, which is the last condition, first of all, we for the amplifier 1, where we state all the information given: power signal input 5 watt, power noise input unknown, bandwidth 400 megahertz, environment temperature 15 Celsius, temperature in chamber 1 33.11 Celsius, and gain 4 dB, which is 2.5119 unitless. Okay, then we repeat the same step for step 1. We convert 15 Celsius to Kelvin, and the formula for Kelvin is Celsius plus 273.15, then we get 288.15 Kelvin. Then we move to the step 2, which we find the power noise input by using the formula K times temperature times bandwidth. Then we get the answer for power noise input, which is 1.590588 exponential negative 12. Then we move to the step 3, where we need to find SNR, which is S over N, or PSI, or we call power signal input divided by power noise input. Then we can get their SNI is 3.1434959 exponential 12. Then we convert the answer of SNI to dB, which is using 10 log 10 time with the SNR. Then we get the answer of dB 124.9741 dB. And then we move to the step 5, where we need to find the power noise initial. So using the same formula, which K time temperature time bandwidth, then we get the answer is 1.6905552 exponential negative 12. Then we find the noise output. We plus a PND, which is initial, plus with the gain times power noise input, then we get the answers 5.6859532 exponential negative 1. After that, find the power signal output, which is gain times signal input, then we get 12.5595 watt. After that, lastly, we find the output SNR for amplifier 1, which is power signal out divided by power noise out, then we get the answer 2.2089 exponential 12, and their dB value is 123.442. Okay, and then we move to the amplifier 2, just doing the same step where we state the information, and then we find the initial noise, which is KTB. We get the answer 1.5671 exponential negative 12. And then noise output, initial noise plus with the gain times power noise out, then we get the answer is 1.954778898 exponential negative 11. After that, find the power noise output for amplifier 2, which is gain 2 divided by gain 2 times power signal out, then we get the answer is 39.7169 watt. Then for step 4, we find the output SNR, which we get 2.0317, and their value in dB is 123.079 dB. After that, the last one, which is amplifier 3, is doing the same step as amplifier 2. We find the initial noise value is 1.560 exponential negative 12. Their power noise out is 4.065555796 exponential 11, and their power signal output is 794.3 watt. And the output of SNR 3 is 1.9537 exponential 13, and their dB value is 123.0909 dB. So that's all for question 1.
Hi, Assalamualaikum. My name is Muhammad Fahmi Yusof. My matrix number is CE190029. So I will continue to explain the possible solution for enhancing the output of SNR. So we are choosing the regenerative circuit or regenerative receiver. So we are using the regenerative receiver is because it's an excellent technique to boost your SNR. Is used to use a regenerator or the Q multiplier circuit, and the signal is number 2 is the signal is amplified before being supplied back into the circuit. So number 3 is this possible feedback has 2 effects. So it's reduced any noise in circuit while also boosting the weak signal. So this is the regenerative circuit. This is the block diagram for the regenerative circuit, and this is the circuit of for regenerative receiver. So this is a simple preamplifier that is used in many ways, such as a radio receiver or shortwave radio receiver particularly lah. So the frequency that approximately is 1.7 to 30 megahertz, and it's using a transistor here, and the resistor is provide drain voltage, and the resistor have and this resistor uh, is provide source of the gate bias, and this is the capacitor. It's blocking to keep the DC signal from here from shortened to the ground lah. So here, so this capacitor is the keeps the output isolated from the uh, direct current lah. The current to this is the amplifier. So if we use only this one, exclude this one. If we use only this and pre-amplifier, it's just to produce the amplitude modulation. For SSB or others, you should have some sort of isolator that bit with the input signal to produce a desired output. There is a so we just we have this feedback here. So this feedback is a positive feedback from the output of the amplifier that cause the circuit to break into isolation at the frequency determined by the variable capacitor. So then the output will be can be an audio frequency such as here is 700 hertz. Can use 700 hertz. So yeah, continue to next slide. So, the regenerative circuits can frequently obtain sufficient gain with just one tube. So, there is no fixed capacitor contributing to the tank. The tuning range is maximized with this approach. So, there will be a couple more band switch position, which is essential for achieving desired results. For the regeneration detector, involve providing an audio output level of hundreds of millivolts using this positive feedback. So, that's all for me. Thank you.
Okay, another method to increase the sound to noise ratio output is by mixing and a local oscillator and a mixer to level shift the impulse signal to another frequency band. Mixing is usually used if you have a certain target frequency that you are aiming for, because it will remove most of the low frequency noise associated with 50 to 60 Hz. It works by literally mixing two signals together that includes the frequency that you are interested in plus a local oscillator frequency. Whenever you combine two frequencies of different value, you don't only get those two frequencies, but you also get the summation and the difference derivative of those two frequencies. So for example, if you have a 100.5 MHz and 89.8 MHz, you not only get those two frequencies, but you also get a 10.7 MHz and a 190.3 MHz from the difference and summation of the two signals. One example application is in the radio industry, which has standardized a specific filter frequency for both FM and AM radio, which happens to be 10.7 MHz for FM and 445 kHz for AM. And because our example is a radio station is in FM, which is frequency modulation, and the other one is AM, amplitude modulation, the 10.7 MHz frequency only allows that the 10.7 MHz frequency to pass from the difference of the original signal, which is the 100.5 MHz and 89.8 MHz signal that have been mixed, and the difference we get 10.7 MHz. And when the filter is used, we will only let the 10.7 MHz frequency to pass. Since the frequency is only produced in the receiver circuit if your target frequency is present, and the frequency of the local oscillator is on par with it will detect that the 10.7 MHz is present, and only the 10.7 MHz will be present because it is the only one that has been filtered. That is another method to increase the sound to noise ratio.
After we gather all the information for enhancing the SNR output from our gathered information, we are choosing based on the possible solution that we have been done. We are decided that the best possible solution enhanced in SNR output without any limitation is using regeneration circuit compared to the mixer and oscillator. It is because using a regeneration circuit has higher frequency bandwidth compared with the mixer and oscillator, which is only 50 to 60 Hz. So besides that, it also have a booster which can boost the weak signal to a higher bandwidth that the mixer oscillator cannot do because it can only filter to a specific bandwidth. Finally, it has better selectivity of bandwidth than the mixer and oscilloscope which have a smaller selectivity. So that's all from our team. Thank you.